This is the first lecture of week 11. So far up to this lecture, we only examined cases where the dependent variable y was continuous. So for instance, average test score or traffic fatality rate has been a continuous variable. But what if dependent variable y is binary? What if y is whether a student gets into college or not, or a person smokes or not, or it could be the dependent variable could be whether the mortgage application is accepted or not. So these are all the cases when the dependent variable is binary instead of continuous. So the example that we're going to look at in this lecture is a relationship between mortgage denial rate and race using the Boston Federal Reserve HMDA data set. So the data set that we have on hand is individual applications for single-family mortgages made in 1990 in the greater Boston area. And there are 2,380 observations, which was collected under the Home Mortgage Disclosure Act. The dependent variable in this case is whether the mortgage was denied or not. And then the independent variables, or the X's, would be income, wealth, employment status, and race of applicant and other characteristics that could potentially impact whether the mortgage application is denied or not. So in this case, because our dependent variable y is binary, when we conduct the linear regression, this is called linear probability model. And basically, it's linear probability model because what we're estimating is probability that y is equal to 0 given x. So in our example, we're trying to estimate what is the probability of an applicant being denied given all these characteristics. When we estimate y hat, it's actually called predicted probability because we're trying to estimate what is the probability of y is equal 1 given x. In other words, we're trying to predict what is the probability of a person getting denied given certain particular characteristics. And the coefficient of interest would be measuring what is the impact or what is the probability that y is equal to 1 for a unit change in x. So in this plot, we're plotting the payment to income ratio against the denial probability. And we have a subset of HMDA data set. So instead of the full 2,000 data observations, we only have 127 observations in this case. And one thing that you notice in this graph is that unlike other scatter plots that we have seen, because the dependent variable is binary, all of the observations all line up on the horizontal line that is equal to 0, y is equal to 0 or 1. And y is equal to 1 means that the mortgage was denied, and when y is equal to 0, it means that the mortgage was approved. So all of the observations are all on this horizontal line of either mortgage being approved or denied. When we're conducting the linear regression, we're trying to fit a linear line that best approximates these horizontal observations. So as you can see here, we're plotting this blue line that minimizes distance between the blue line and the individual black dots. So let's say we have estimated the linear probability model using the full HMDA data set. And running this model in Stata, we obtain this regression coefficient. So let's say that we want to know what is the predicted value of being denied when PI ratio is 0.3. As we have done in the previous cases, we just plug in the PI ratio of 0.3 into the model to obtain the predicted value of y. Let's say that we want to measure the effect of increasing PI ratio from 0.3 to 0.4. One way to do this is calculate the probability of being denied when the PI ratio is 0.4. So plug in 0.4 into the model to get the predicted probability of being denied, which in this case is 0.16 or 16%. And then whatever the difference between the two would be the effect of increasing PI ratio from 0.3 to 0.4. So in this case, the difference is 0.06 or 6 percentage point. So to put it in other way, if PI ratio increases from 0.3 to 0.4, the probability of application being denied increases by 6 percentage points. Because this is a linear model, we can simply calculate the change from 0.3 to 0.4 by simply multiplying the coefficient of PI ratio to the change of PI ratio to get the same number. And this is only possible because our model is linear. So next, let's assume that we want to include a binary variable of an applicant being Black as additional regressor to the previous simple linear regression model. So here we estimated the model, and from Stata we obtained this coefficient 0.177 for the binary variable of an applicant being Black. Let's say we want to estimate what is the probability of being denied if an applicant is Black versus white, given that PI ratio is 0.3. So we plug in PI ratio 0.3 to the model and estimate for Black applicant, the binary variable would be 1, and for white applicant, the binary variable of Black would be 0. And then by plugging this in, you can measure the probability of being denied for a Black applicant versus the white applicant. The difference between these two probabilities shows that Black applicant with the PI ratio of 0.3 is 17.7 percentage points more likely to be denied than a white applicant with the PI ratio of 0.3. We can also see that the difference between these two probabilities is essentially the coefficient. So the coefficient of this Black binary variable measures what is the effect of being Black on denial rate compared to the omitted group, which in this case is white applicants. And the coefficient is also statistically significant. So it seems like being Black applicant affects the denial rate, but we can also think that there probably is omitted variable bias because we are only including in this model just 2 control variables. So there are several advantages and disadvantages of using the linear probability model. So some of the advantages of linear probability model is that it's really easy to estimate and interpret. And also the inference is the same as for multiple linear regression. So how we look at the standard errors and how we decide whether it's statistically significant or not is basically extension of what we've done in multiple linear regression model. Of course, you do need to use the heteroscedasticity robust standard errors when you're estimating the model in Stata, but otherwise, it's really simple to estimate and interpret the coefficients. Some of the disadvantages of using linear probability model is that linear probability model, because the model is linear, predicts that the probability for a given change in x is the same for all values. So in other words, in the case of a HMDA example, when the PI ratio increases from 0.8 to 0.9, how much the denial rate increases is same as when the PI ratio increases from, say, 0.3 to 0.4. And this may not necessarily make sense because if your PI ratio is already really, really high, then your probability of being denied is not going to change much, if any. But if your PI ratio is kind of low, so say your PI ratio is 0.3, and then if it increases to 0.4, maybe this would increase the probability of being denied much more. So we can see that in this particular case, having a linear model may not necessarily make sense. Also, another disadvantage is that because of the nature of the model, sometimes when you calculate the predicted probability of being, say in this case, denied, it can actually be less than 0 or greater than 1, which doesn't make sense because when we think about probability, it always ranges between 0 to 1. So we cannot really, it doesn't really make sense to think that a probability can be higher than 100% or less than 0%. So some of these disadvantages can be actually resolved by using a nonlinear probability model. And we're going to explore these two different nonlinear probability models in the next lecture, which is called probit and logit regression.